Hello and welcome to today's video where we're going to be figuring out how to determine a rejection region based off of a predetermined alpha. Let's get started. Let x be a Bernoulli random variable with probability of success q. You want to perform the following hypothesis tests. H null is q equals 0.75. H1 is q is greater than 0.75. We will reject H null in favor of the alternative if the summation of xi's from I equal 1 to 30 is greater than or equal to k. Calculate the smallest k such that the significance level of this test will be at most 0.02. In this problem, it's actually extremely similar to the previous problem, question 21 of the spring 2019 exam. See the little I in the top right corner of this video if you want to jump to that. And we're really going to be using a lot of the same required knowledge, which are continuity corrections and central limit theorem. So again, central limit theorem, suppose x1 to xn, a sequence of IID random variables with expected value of xi equal to mu, and the variance of xi equal to sigma squared, where it's less than infinity. Then, as n approaches infinity, the random variable square root of n of x bar sub n minus mu converge in distribution to a normal 0 sigma squared. So, visually, just what this is saying is we're taking a Bernoulli sample of size 30. And if you were to do that a bunch of times and take a histogram, it would closely map to this normal curve. And as you increase your sample size, it's going to become more and more similar to its corresponding normal curve as determined by this square root n adjustment here. Second, continuity correction. So this is saying and recognizing, first off, in a sample size of 30, where each sample can either be a 1 or a 0, that means we only can see whole numbers. So we might get 30 ones, we might get 29, 28, 27, 26, so on and so forth. But with this normal approximation, so it's going to be normal as n approaches infinity. So what we choose to do is use a normal distribution to approximate what we're actually going to see, even though n isn't infinity, and that shows up in this discontinuity, right? So here you can have a 27 or you can have a 28, but it's actually impossible to have anything in this orange region. So when we pick our critical region, which, spoiler alert, our answer is going to be 28, what we're going to do is actually subtract off 0.5 because we want to allow half this area to count to 28 and half this area to count to 27, because it has to be assigned to one or the other, and we're dealing with discrete data. So this is just our approximation for the Bernoulli samples. So jumping into the problem, what we're going to do is the mean of our null. So we're assuming our null hypothesis, so 0.75. We then, using our z table, look up what corresponds to, let me see here, an alpha level of 0.02, or I'm guessing it would be 0.98 using the z table, because I believe it uses the high end and the area to the left. And when you do that, you see a z statistic of 2.055. We then multiply by our variance. So a variance of Bernoulli is going to be probability of success times the probability of failure. And then, again, that square root of n adjustment, due to the CLT, we're going to be taking the square root of the variance divided by the sample size 30. And then finally, that needs to equal k minus 0.5 divided by 30. So whatever our critical region is, we want to be 2.055 standard deviations above 0.75. And as we mentioned in this visual here, let's say our rejection is 28. Well, if that were the case, we want this right of this vertical line orange to count towards the area, because we want to do this continuity correction. So that's why it's k minus 0.5. And then all of that divided by 30. So here we're just solving for k. We get 27.87. And then if we go back to the beginning of the problem, we see that we want what is the smallest value of k such that the significance will be at most 0.02. So as we, what would this be? So as we decrease k, that's moving this line to the left and increasing the area to the right. And if we increase the area to the right, we're, instead of going to be at exactly 0.02, going to be at a value larger than 0.02. And we want to stay under that. So we know that we have to round up, not down, which is why our 27.87 needs to be pushed up to 28, which is our final answer. And scrolling up, that is C. So I have two additional comments, even though we've just finished going through the problem. First, similar to as previously mentioned, the question immediately before this, question 21, whether or not you do the continuity correction, you actually get the same answer. So still not sure if that's always going to happen or if it just got lucky. I really wish they would specifically call out you need to do a continuity correction, but I would say for the purpose of the exam, assume you have to do it. And then the second additional note is the sample sizes we're dealing with here actually allow you to not have to approximate. So alternatively, we can again understand that when we say alpha is 0.02, we're saying the probability that you reject the null under the assumption the null hypothesis is true is 0.02. So that's just to say, assume that the success rate is 0.75. What's the probability of seeing 30 successes plus seeing 29 successes and 1 failure plus ... until you hit whatever that number is that puts you over 0.02. So the reason why you might do this, just speaking strategically here, is because when you look at this problem, you see that you're only going to have to go to 27. Worst case scenario, if the answer is A, you're only going to have to calculate for, I guess, maybe a fifth probability. But that's relatively simple, even by hand. Second, if you're watching this video soon after it comes out, the first sitting of this post-pandemic MAS1 includes a Excel-like feature in the online exam, and so it's actually not going to be too difficult to type this out and then drag and fill based off of different X's. So even if we were doing this by hand, this is still a viable option, but even more so when we have access to essentially Excel during the exam. So this is definitely a viable alternative. And here you're just doing, what's the probability of seeing 30 successes? Well, how many ways are there to organize 30 yeses? There's only one. 30 choose 0 is 1, multiplied by the probability of seeing 30 of these, and then 0 of those. So 0.75 to 30, multiplied by 0.25 to the 0, so you have 0 failures, and that equals this number. Next, 29, there are 30 ways to organize 1 failure, and then you just change these numbers. So there are 29 successes and 1 failure. You get a new probability, and you repeat this process. So how many ways are there to organize 2 failures, so on and so forth. And what you do is then calculate the running sums, because the alpha is going to be, if whatever the critical region is, the summation of all the probabilities at that point to the right. And what you see is when you sum these 3 numbers, 28, 29, and 30, you get a little over 1%, so that is under our 2% alpha threshold. But if you add one more, the 27, you then go past the threshold. And that's why we know, again, just a different way of coming to the correct solution of 28. And in the event that this and the continuity correction disagreed with one another, this answer is exact, whereas this answer is an approximation. So just something to keep in mind, that I don't anticipate this happening, but if it did, you would want to go with this answer. So again, just to reiterate, the final answer is C. So thanks again for watching. Really appreciate it. And if you have any ideas of additional content corresponding to MAS1 you would like to see, separate from just my general walkthroughs of questions, please let me know in the comments, and I'd be happy to consider doing them. So, thanks. Have a good one.